All right, hello physical science students, and welcome to this video lecture that's going to introduce you more formally to work and power. We did a lab today where you got running around up and down stairs to figure out how much work you did and how powerful you were. So now we're going to try and understand a little bit more about what work and power actually are. So first and foremost, our verbal definition for work, it's kind of not really a definition, but just understanding when work is done. So we say that work is done when a force acts on an object to actually cause that object to displace itself. So that object actually has a displacement. Now, just like anything in physics, we have a mathematical definition as well, where we're going to say work is equal to a force parallel. Okay, that force parallel is key, times a displacement. Now our units for work, if we relate back to our unit on forces, we know that our units for force are newtons and our units for displacement are meters. Now we could say that our units for work are a newton times a meter. However, we simplify those and we say that the unit for work is called a joule, and we abbreviate that with a J. Now, moving on, we have some different types of work. The first type of work that we have is positive work. Now, what positive work is, we say that positive work is being done when the force is applied in the same direction as displacement. Okay, so an example of this, a box is being pushed to the right, that applied force is also going to the right, so that force is being applied in the same direction as the displacement in that case. Both the force and the displacement are to the right. Now, negative work is done when the force is applied in the opposite direction. Okay, so force applied in the opposite direction of the displacement. So an example that comes to mind here would be, for any of you softball or baseball players out there, you slide into home plate. Well, your displacement is towards home plate, but the force being applied on you is actually the force of friction, which is going the opposite way. So in that case, the force is opposite your displacement, therefore negative work is being done on you. Now, zero or no work is kind of an interesting case. Zero or no work would be force applied is perpendicular to the displacement. Okay, now an example that comes to mind for this one would be, let's say that I'm a waiter at a restaurant and I'm carrying a tray of food across the dining room. Well, the force that I'm applying to that tray of food is upwards. Okay, so there's the force that I'm applying upwards on the tray, but my displacement is actually horizontally across the room. Okay, so in that case then, that force is perpendicular to my displacement. Therefore, no work or zero work is being done. Another example of zero work would be we apply a force to something, but there is no displacement. So if we take a look at our equation up here, if my displacement is zero, well, then my work is going to have to be zero as well. And this could be you lean against a wall. Okay, you're applying a force to the wall doesn't move, so zero work is being done on the wall. Okay, so in the coming days, we're going to take a look at a bunch of different scenarios and determine types of work, determine the actual quantity of work being done. The next slide is going to go through power. All right, so moving on from work, what is power? And power is the rate at which work is done. Now that term rate should not be new to any of us. We used that term quite a bit in our first unit when we were talking about velocity or acceleration. Velocity was the rate at which an object displaces itself. Acceleration is the rate at which velocity changes. So when we think about rate, we think about a certain quantity and how it changes in a certain amount of time. So based on that, power is equal to work divided by time. Okay, how much work do we do in a certain amount of time? Now our units for power, our units for work were joules, and our units for time are seconds. Now we could say that power is a joule per second, but we again simplify that, and our units for power we say our units for power are watts, and we abbreviate that with a W. Don't confuse W for watts and W for work. Okay, we like to use the same symbols in physics. I think it's just to confuse people. But anyway, the main thing that I want us to know with power is how power can change based on these two variables. Okay, so because work is in our numerator, if work increases, well, then power also increases, okay? If work decreases, then power decreases. Now, conversely, if time increases, because time is in our denominator, if time increases, then power decreases, okay? And then vice versa. If time decreases, then power increases, okay? So power is pretty simple. We're not going to be going too in-depth with power, but I do want us to understand the value that it has when we're talking about work, and then just being able to manipulate this equation that we have for power and understand how power can change. But in the coming days, we're going to focus primarily on work, and then we're going to delve into how work can actually impact objects and objects' energy. We haven't talked about energy yet, but we will. So with that being said, have a good rest of your night, physical science students, and take care.